We're going to look at 14.4, which is the change of concentration with time, which is dealing with first order and second order reactions and how your concentration changes as your reaction proceeds. So, if we look at first order reactions, remember that our rate depends on the concentration of the reactant to the first power. That's a first order reaction. So if my concentration doubles, my rate will double. Or if the concentration triples, my rate will triple, that kind of thing. So that's what we're looking at, and we're going to use a little bit of calc and a little bit of graphing to look at exactly how I can tell whether something is a first order or whether something is a second order. So these are the ones where your concentration is the first power. So the rate, which is the change in concentration over time, okay, is K, my constant, times A, concentration to the first. Okay, we call these a differential rate law. If I want to use what is called an integrated rate law, where we use a little bit of calculus and we're going to rearrange things, you actually got to integrate. Okay, we don't get all into exactly how that all works with this. We're going to tell you what it comes out to be. You're going to end up with a natural log of A at some time t is equal to negative K times t plus the natural log of the concentration of A initially, or see at 0 because that's the start time. Okay. So when I go to graph this later, we're going to figure out exactly where we're going to see a straight line, because this is our integrated rate law. It's after you do some integration. Okay. So originally, if I were to graph this, I would look at how my pressure or my concentration changes with time, and you get this kind of a curved graph because the rate's going to change as my time goes on. Your rate gets slower and slower and slower. Well, in order to tell if it's first order or not, we use this integrated rate law here, and I'm going to have this being my y. This is going to be my m. That's going to be my x, and then this is going to be b, which would be my y-intercept. So that would be this graph here on the right. Notice how it is a straight line. If something is a first order reaction, the natural log of A versus time will be straight. So if I take and I graph the natural log of my concentration times time, I'm going to get a straight line if it's first order. And also then, my slope is my constant for the rate K. It's only for first order reactions though. Okay, if you look at a second order reaction, those are where your concentration is raised to the second power. If I take my differential rate law again, which is this, the rate being equal to change in concentration over time, is equal to my constant K times A squared, change it to my integrated rate law. It's a little bit different because it's squared. What we come out with here is that my 1 over the concentration at some time is going to equal to K times T plus 1 over the concentration of A initially. So it's a little bit different. So on this one, the y equals my mx plus b. My m is still my rate constant K, but I'm going to get 1 over the concentration versus time to be straight. So if something was a second order reaction, if I were to graph the concentration or the inverse of my concentration versus time, I would get a straight line. If it was not a second order, I would not get a straight line. So look at an example. So the following data was obtained from the gas phase decomposition of nitrogen dioxide. They give the reaction, and they want to know whether it's first order or second order. So what you got to do is figure out the natural log of NO2, and then look at what numbers when I graph these, whether it's going to be straight for which one of those two. Okay, so what you want to do is you want to graph these. So I want to have time versus the natural log, and then I want to have time versus 1 over. You can also kind of look at these numbers and figure out which ones are having the same change in concentration each time. And if I look at this second one here, I'm going to go by 27, and then 27 more, and then roughly 27, and then roughly again. So it's roughly the same change in delta concentration for NO2 each time. So it's going to be second order reaction. If you don't believe it, if you're not sure, just graph the numbers on your graphing calculator and it'll show you that one is actually the straight line. So this one is second order, because that would be a straight line for that one. Okay, half-life. Okay, half-life is the time required for the reactant to reach half of the initial amount that you have, it describes how fast the reaction happens. If you have a short half-life, you tend to have a fast reaction. Okay, if it is a first order reaction, then your half-life actually doesn't depend on the starting concentration. Your half-life actually remains constant throughout, and this has to do with the fact that when you compare your half concentration to the initial concentration, you end up with just the K, your constant, times the half-life time. And when you do that, you end up taking the natural log of a half, and that's going to be equal to negative K times T. Well, K is a constant. The natural log of a half is 0.693. So when I end up solving for a half-life, this is my equation, or how you figure that out. This is on your green sheet. That is the T to the 1/2 equals 0.693 over K. And like I said, that comes from kind of solving that integrated rate law that we looked at just a little bit ago. But this picture here just shows you that if I go from 150 to 75, that has the amount of time right here, about 12,000 seconds or so for the first half-life. Then to go from 75 to 37.5, that next half-life goes from maybe 28,000 to 12,000. Okay, so it's how much time it takes for half to get lost. Okay, the last thing here is my second order reactions for half-lives. Okay, your half-life concentration, or your half-life, depends on the reactant concentration, and then therefore it changes as the reaction proceeds. So as a first order reaction, doesn't matter what my concentration is. A second order reaction actually does care what your concentration is. Okay. And as your concentration decreases, the half-life increases, and we end up with T to the 1/2. It's going to be equal to 1 over the constant times the concentration of A initially, or originally. And the lower the concentration, the longer the half-life. The longer it takes for half of it to get used. Okay. So it says the reaction of C4H9Cl with water is a first order reaction. You have a chart. It shows how it changes with that particular time. This is the chart from way at the beginning of the chapter. It says from the graph, I want to estimate the half-life for the reaction, and then I want to use the half-life to try and find the rate constant. Right? Well, I know this is a first order reaction. We talked about this before. Okay, so initially, for A, my concentration is 0.1. Well, I want to know when half of that. So my half-life is going to be when my concentration equals 0.05 molar. Well, where does that occur? Well, 0.05 right here occurs somewhere right around, say, 340 seconds. That's my guess, somewhere in the middle there, okay? And I'm going to use my half-life from A to then calculate my rate constant. Well, rate constant K is going to equal to the natural log of a half, which is 0.693, over my half-life, which is 340 seconds. So my rate constant K is 2.0 times 10 to the negative third seconds to the negative first, because seconds are on the bottom, and I don't have a unit for this natural log of a half.